Hi, my name is Dan Shultz, and today I'll be talking a little bit about vector spaces. But before we begin, let's go over an overview of what I'll be covering in this video. First off, we'll be taking a look at vector spaces, the definition, its axioms, and some examples. We'll take a quick look at subspaces. We'll do a quick review of some things from linear algebra, such as linear combinations, spanning, and linear independence. We'll then put those together when we look at what a basis is, and finally we will go over what the dimension of a basis is. So you might be asking, what is a vector space? Basically, a vector space over a field F is a set V together with two operations that satisfy 10 axioms that we'll go over in a minute. Elements of set V are commonly called vectors, and elements of set F are commonly called scalars. The first operation is vector addition, and the second operation is scalar multiplication. As I'm going over the axioms, make sure to pay special attention to the first 5 axioms, as this may be something you've seen before. The first axiom we're going to need is closure under addition. The second axiom we're going to need is associativity of addition. For the third axiom, we are going to need an identity element for addition. For the fourth axiom, we are going to need elements to have inverses for addition. And for the fifth axiom, we're going to need commutativity of addition. Now we still have a few more axioms to go to be a vector space, but if you look at the set V and the addition operation, you can see that V is an abelian group under addition. So what else do we need to be a vector space? We're going to need closure under scalar multiplication. So if we take a scalar and multiply a vector, that is still going to result in a vector in set V. We're going to need scalar multiplication to distribute with respect to vector addition. So if I have a scalar times a quantity of a vector plus a vector, that's going to be equal to a scalar times a vector plus a scalar times a vector. We're going to need scalar multiplication to distribute with respect to field addition. So if I have a quantity of scalars times a vector, that is going to be equal to a scalar times a vector plus a scalar times a vector. We're going to need scalar multiplication to be compatible with field multiplication. So if I have a scalar times a quantity of a scalar times a vector, that's going to be equal to, if I were to take those two scalars, multiply them, and then use scalar multiplication on the vector. And lastly, we are going to need an identity element for scalar multiplication. If all 10 of these axioms are satisfied under the two operations for V, you have a vector field V under the field F. Let's look at some examples. The first example is trivial, where V equals only the 0 vector. Another example is when V equals the field itself. And a third, little bit trickier example is when V equals the set of all 2 by 2 matrices, where we have vector addition defined as matrix addition, and scalar multiplication defined as matrix scalar multiplication. Now let's go back to our axioms from earlier to verify that the set of 2 by 2 matrices is a vector space under, let's say, the real numbers. We know that the set of 2 by 2 matrices will be closed under addition, because if you add two 2 by 2 matrices with matrix addition, you're going to get another 2 by 2 matrix. Since the numbers inside 2 by 2 matrices are just real numbers, we know that it's associative for addition. We have the matrix 0, 0, 0, 0, so we have the identity element of addition. Since we have the negatives, we know we have inverse elements of addition. And since matrix addition is similar to regular addition, we know that it will be commutative. For the next 5 axioms, we know that if we take a scalar and multiply a 2 by 2 matrix, using scalar multiplication, we're going to get out another 2 by 2 matrix. Now the next 3 may not be as easy to see in your head, but because we know we are working with matrix addition and scalar multiplication, it's easy to see that we are just using regular addition and multiplication for each number inside the matrix. And for the last axiom, we have the identity element. Now let's take a look at subspaces. We define W to be a subspace of V, written W less than V, if W is a subset of V, and W is also a vector space. Now, a little hint, because W is a subset of V, certain axioms are inherited, leaving only the following to be checked, and you can prove the other ones if you don't believe me. If U and V are vectors in W, then U plus V has to be in W. And you also have to check that if k is any scalar and u is any vector in W, then k times u is also in W. Now let's do a quick review of some things from linear algebra, first being linear combinations. Remember, a vector W is called a linear combination of the vectors v1, v2, all the way through vn if it can be expressed in the form W equals k1 times v1 plus k2 times v2 plus on and on up to kn times vn, when we know that k1, k2 all the way on through kn are scalars. Now if we take a look back at what we know from spanning, if set S is a set of vectors in a vector space V, then the subspace W of V, consisting of all linear combinations of the vectors in S, is called the space spanned by v1, v2, on and on up through vn, and we say that the vectors v1, v2, all the way up through vn span W. To indicate W as a space spanned by the vectors, we write that W equals the span of S, or W equals the span of the individual vectors that span W. The last thing we're going to review is linear independence. If we have a set S that is a non-empty set of vectors, then the vector equation k1 times v1 plus k2 times v2 on and on up to kn plus vn equals a zero vector has at least one solution, mainly that all the coefficients equal 0. If this is the only solution, then S is called linearly independent. If there are other solutions, then S is called a linearly dependent set. Now, taking what we just reviewed with linearly independence and spanning, let's take a look at basis. If V is any vector space and S is a set of vectors in V, then S is called a basis for V if the following two conditions hold. S has to be linearly independent and S has to span V. So let's look at an example. If we have V equal the set with elements looking like A plus B times root 3, such that A and B are rational numbers, and F equal the set of rational numbers, we can see that the elements are going to look like some rational plus a rational times root 3. So what subset of V do we need to have a basis? Well, we know it's going to need to span and be linearly independent. So in order to span the set of elements that look like A plus B root 3, which can also be called the set of rationals adjoined root 3, we know that we are going to need some rational number that we can use through addition and multiplication to get the rest of the rational numbers, and we will also need root 3 and all of its multiples. So when we look at what the basis is for this, we can see that if we have the elements 1 in the square root of 3, that we can generate all of the elements in Q adjoined root 3. We also need to check if it is linearly independent, which is easy to see as we just went over, where 1 is rational and the square root of 3 is not. So let's take a look at the dimension of a vector space. The dimension of a finite dimensional vector space V, denoted by dim, and the subscript is f of V, is defined to be the number of vectors in a basis for V. In addition, we define the zero vector space to have a dimension 0. So basically, what a dimension is the number of elements in a basis. So when we look back at the example we just went over, where we had the set of elements A plus B root 3, such that A and B are rational numbers, over the field of all rational numbers, we saw that our basis was made up of the elements 1 and the square root of 3, and so we can easily see there that the dimension of this is 2. Thank you for watching. This has been Dan Shultz's talk on vector spaces.